So as I've talked so far about these neuromorphic systems, so there's a need to think about for such a system. We need sensors, right? The sensors can sense the outside world, and that input comes into this network architecture, which can process those inputs and then come up with the inference or whatever that we're trying to do. Now, this network architectures certainly have to be implemented in the right kind of hardware, as I mentioned. Could be a von Neumann hardware, or could be a hardware which is more geared towards better implementing neuromorphic systems. And finally, one has to think about the circuits and the devices that one can use. So the question, of course, is, can we take any cues from the brain? Because at least we know that the brain is reasonably efficient. So to that effect, the question then becomes, what are the cues that I can potentially take from the brain? How about the neuron models, the learning algorithms, the network topology? We talked about each of those things. And finally, the computing principles of the brain, whatever little that we know of it. So going a little bit more details of the cues that we can potentially take from the brain, let's try to look at the neuron model. So there are different types of neuron model that people use today. And the deep learning, for example, and we'll go into that in just a minute, they use the activation function, which is a ReLU activation, could be a sigmoid activation, and so on. But more biological ones are more like the leaky integrate and fire kind of neuron. And if we go and make it into even more bioplausible, we probably have to use the Hodgkin-Huxley model and so on. Now, in some of those cases, unfortunately, we don't really know how to utilize all the details of these Hodgkin-Huxley model. So maybe it makes sense to make some approximations and use maybe a leaky integrate and fire neuron or an integrate and fire neuron, and we'll go into that in the next few slides. The next thing that turns out to be quite important is the fact that the learning algorithm. And today, as we'll see later on, most of the learning algorithms use what's called backpropagation. It has a good theory behind it and can optimize pretty well, but it takes a good amount of time. Now, also local learning, rather than backpropagation, local learning has also been observed in the brain. And to that effect, there are different kinds of local learning algorithms. And we'll talk some of those local learning algorithms to see if we can actually achieve the kind of performance that, for example, some of these backpropagation based techniques do. Finally, also, if we look at learning, and in today's deep learning, in particular, actually, if you're trying to learn, for example, images or videos, it turns out that we humans do it in a little bit different way than what today's deep learning, the standard deep learning does. We do what's called foveation. We are able to actually focus on a particular object, and we can ignore the background. And then we also have something called rapid eye movement, which are saccades, and by those rapid eye movements, we can actually go around and figure out what different objects are in a particular scene. So the question, of course, is if I can potentially use some of those techniques, potentially I can have better learning. Now, the next thing that is also important is that the network topology. So what kind of network topology should I use? And those of you have been using deep learning, people have been using, for example, VGG16 or a ResNet 20 or other kinds of architectures. The question then really becomes, what kind of network architecture is good? Should I have feed-forward connections? Should I have backward connections? And so on. Are those feedback connections necessary for the kind of applications that we're looking at? So those are the different or interestingly important questions that one has to answer. And do they mimic? And for example, in this particular case, if you're looking at images and video, do they mimic the visual cortex of our brain? That is also kind of important, and not that plausibility is important. It's really a means to an end, we hope. We know that the brain is reasonably efficient. So our hope is that if we make it more bioplausible, then we can achieve hopefully better accuracy and at the same time better energy efficiency than what we can do today. Finally, what about the compute principles of the brain? We certainly know that the architecture of the brain is not like a von Neumann architecture, the hardware architecture of the brain. And we also know that compute in the brain in some ways is done in an integrated fashion within the memory itself. We may not understand the memory organization that well, but at least we know that there is not a separate compute unit and a memory unit. They're all integrated together in some interesting ways. So the question then is it possible that I can do some compute in memory kind of computations and get efficiency? Because in today's von Neumann architecture, one of the problems that we face is the fact that we have to go and fetch data from the memory, bring it to the compute unit, do the computations, and then bring it back to the memory again. And it turns out that kind of data that moves back and forth between the memory and the compute unit can be quite cumbersome, not only cumbersome, but cumbersome in terms of power consumption. The power consumption goes high, and at the end of it, the latency suffers. So with all those in mind, let's go into a little more details of, for example, the neuron model and the learning algorithms, and then we'll come back to network architecture and the hardware architecture required for doing brain-inspired computing. To start with, let's think about the neuron model. And if I were to talk about a biological neuron, which I'm showing here, where I'm showing basically the cell body, the axons, the synaptic connections, and so on. Now, it turns out that when a bunch of inputs that are coming in to a biological neuron, which are in form of a spike, which I'm showing at the bottom, the input spikes coming to the neuron, the membrane potential of the neuron goes up when a spike comes. However, if the membrane potential actually decays, if there are no spikes are coming in. But if there are more spikes that come in, again, the membrane potential goes up. And beyond a certain point, when there are enough number of spikes and the membrane potential goes to a certain threshold level, the neuron spikes. And then the membrane potential is reset to, again, 0, and the operation starts all over again. Now, that particular operation, one can certainly represent it in terms of a standard CMOS circuit, an RC circuit, and what I'm showing here is basically how the behavior of such a neuron can be represented by just a simple RC circuit, where I end up charging the capacitor, and the capacitor decays, and then it gets charged again as new input comes in. So. Now what one can also do is, rather than having a leaky integrate and fire kind of neuron that I just mentioned here, it's possible to say that, hey, can I make some approximations? So what kind of approximations I can make? I can potentially say that, hey, can I get rid of the leak? Now, if I get rid of the leak, then I have an integrate and fire neuron that I'm showing here. And this integrate and fire neuron usually would have a little more spiking activity than what I would have in a leaky integrate and fire kind of neuron. And we'll see that leak certainly plays an interesting role in some of these applications. We'll go into that in just a minute. Then also one can potentially think of having the neuronal activation function to be given by, for example, a sigmoid. Now, interestingly, in this particular case, I'm actually showing a stochastic sigmoid. Meaning thereby that when an input comes in, an input could be in form of a current, let's say, to that neuron, the output of the neuron switches, but switches with a probability which is given by that sigmoid function that I'm showing there. Now this, if you think about it, it also behaves like a digital or a spiking neuron. Whenever there's a right kind of input that comes in, it switches with the probability. And the reason I'm showing this neuron is because some of the devices that we have today have such probabilistic sigmoidal switching behavior. So that can potentially be useful later on for using it as an activation function of a neuron. Now, today's deep learning, the standard deep learning that they do make several approximations. While they are certainly biologically inspired or weakly inspired by the neurons of the brain, here I'm showing the approximations that they have made. In fact, I'm showing a ReLU neuron, which is a rectified linear unit. It has nonlinearity, as you can see. But the basic idea for having such a ReLU neuron, or for example, one can potentially think of a tan hyperbolic neuron too, as an activation function. The reason why those kind of activation functions are used is because we'll see later on that they're differentiable, and differentiability has an important impact when it comes to training of some of these neural networks. We'll see that activation functions like leaky integrate and fire kind of neuron or an integrate and fire kind of neuron would have some interesting implications because they are not differentiable. So training, we'll have to make some approximations as we'll see later on. Now, I'm highlighting these ReLU neurons and tan hyperbolic neurons because they are kind of used a lot in standard deep learning. Whereas on the left side of it, I'm showing these leaky integrate and or integrate and fire kind of neuron, which are more suitable for a little more bioplausibility, could be for the spiking neural networks. One of the differences that you also see between the left neurons and the ReLU neurons, or the leaky integrate and fire and the ReLU neurons, is the fact that there is something called a membrane potential that we have in case of the leaky integrate and fire neuron, and this membrane potential stores information, as you can see, from the past. And that information goes away and propagates in terms of a spike when the neuron fires.